What really happened during Earth's deadliest hour, the Triassic Collapse? Molten rivers tore across the supercontinent of Pangaea, while skies choked with ash and clouds of sulfuric haze blotted out the sun, casting a world into shadow. It was the late Triassic, a time when Earth's ecosystems teetered on the edge of collapse, and life, both fierce and fragile, faced unprecedented stress. Oceans suffocated under oxygen-starved waters. Forests burned to cinders, and the giants of the land stumbled toward extinction. What unseen forces orchestrated this planetary catastrophe, and how did life respond to the deadliest hour in Earth's history? Join us as we descend into the unfolding chaos of the Triassic Collapse. Before the breaking point, life on the edge of stability. Across the sprawling breadth of late Triassic Pangaea, an immense supercontinent unified by arid interiors and storm-lashed coasts, life thrived in a precarious equilibrium that would later reveal just how delicate its foundations truly were. Vast river systems, driven by the mega monsoon that dominated the era's circulation patterns, carved through red-hued floodplains where coarse sandstones and mudstones accumulated in seasonal rhythms, leaving behind sedimentary records that modern geologists use to reconstruct the planet's pulse in the final moments before catastrophe. Towering conifer forests, dominated by genera such as Araucarioxylon and Voltsia, anchored these landscapes, their resinous trunks rising above a mosaic of cycads and ginkgophytes that flourished in pockets of relative moisture, despite the supercontinent's overarching aridity. The climate, though warm by modern standards with global averages exceeding 22–24 degrees Celsius, oscillated between prolonged droughts and heavy monsoonal outbursts, creating habitats that rewarded the resilient yet punished the fragile. Along the margins of these shifting ecosystems, immense archosaurs, rulers of the late Triassic, established themselves as the unrivaled masters of terrestrial dominance. The semi-aquatic phytosaurs, exemplified by robust forms such as Rutiodon and Mystriasuchus, patrolled the braided river channels with elongated tooth-lined jaws that mirrored the morphology of later crocodilians, but represented an independently evolved design optimized for ambush predation. On drier floodplains, heavily armored atasaurs, like Desmatasuchus, browsed low vegetation using shovel-shaped snouts adapted for digging, their dorsal spikes forming a natural barrier that discouraged even the most determined predators. Yet the true apex threats were the Rauisuchians, colossal carnivores such as Postosuchus, whose deep skulls, serrated teeth, and pillar-erect limb posture allowed them to move with a terrifying blend of stability and power, contrasting sharply with the sprawling gaits of more primitive reptiles. Nearby, early dinosaurs, still small, still overshadowed, still far from dominance, occupied marginal niches that placed them at the periphery of ecological power. Slender-limbed forms such as Coelophysis hunted in packs or loose aggregations, as suggested by mass death assemblages in the Chinle Formation of the American Southwest, indicating both social behavior and the hazard of drought-driven congregation around shrinking water sources. Slightly larger herbivorous species, like Plateosaurus, ranged across Central Europe's Triassic basins, using elongated necks and flexible feeding strategies to exploit vegetation in environments where seasonal variability demanded adaptability. Fossilized bone histology reveals their rapid growth rates and cyclical deposition patterns, suggesting that these early dinosaurs were physiologically capable of enduring unpredictable climates by modulating metabolism, a survival advantage that would later take on profound significance. In the marine realm, the teetering balance of life becomes even more apparent when examined through the fossilized remains of hyperdiverse ammonoid lineages and the ecological structure of Triassic seas. Ammonoids such as Choristoceras, Siloceras, and Arcestes proliferated in extraordinary abundance. Their intricately patterned shells recording chemical signatures, particularly variations in carbon and oxygen isotopes, that reflect cyclic fluctuations in ocean temperature and carbonate saturation. Marine reptiles, including the broad-bodied placodonts and streamlined ichthyosaurs, prowled coastal shelves and open waters respectively, maintaining complex food webs that relied on a steady supply of planktonic productivity. Reef systems, constructed not by corals but by sponges, microbialites, and early scleractinians still recovering from the Permian devastation, stitched together shallow marine environments where biodiversity flourished, yet remained conspicuously sensitive to even slight changes in water chemistry. Far inland, sediment cores extracted from Triassic lakebeds reveal microfossil assemblages that reinforce the impression of a world perched at the edge of climatic stability. Pollen spectra show alternating dominance between drought-tolerant conifers and moisture-dependent fern groups, indicating flip-flop transitions in hydrology that occurred on millennial scales and correspond to orbital forcing cycles identified in the Newark Basin's cyclostratigraphy. Charcoal fragments preserved within these cores demonstrate that wildfire activity was both frequent and intense, driven by high atmospheric oxygen concentrations estimated at roughly 18–20%, a level sufficient to fuel continent-spanning forest burns that reshaped ecosystems through periodic pulses of destruction and regrowth. These fires, in turn, influenced soil nutrient dynamics, periodically reducing biomass but also creating brief windows of ecological opportunity for opportunistic species that thrived in disturbed habitats. In regions closer to the equator, the immense monsoon system that blanketed Pangaea produced seasonal rainfall deluges so powerful that they sculpted entire sedimentary basins into rhythmic sequences still visible today. Each year, colossal storms deposited thick layers of silt and clay across ephemeral lakes, generating valve-like laminations that geologists use to measure subtle climatic oscillations across tens of thousands of years. During the dry season, desiccation cracks formed polygonal networks on exposed mudflats, while the retreating waters concentrated dissolved minerals into evaporite deposits, particularly gypsum and halite layers that record extreme aridity episodes in the Coleraine geological archive. These alternating wet-dry cycles created ecological bottlenecks where only the most drought-tolerant plants, amphibians, and small reptiles could persist, driving evolutionary selection pressures that favoured species with broad ecological tolerances or efficient water conservation strategies. Elsewhere, across the vast supercontinent, the interplay of tectonics and climate produced isolated pockets of endemism that highlight the fragmented nature of Triassic biodiversity. Rift valleys within what would become eastern North America hosted lush lowland ecosystems that supported a mixture of amphibians, temnospondyls, and smaller archosaurs whose physical adaptations reflected local environmental demands: broad skulls for bottom feeding, elongated limbs for navigating swampy terrain, and dermal armour for deterrence in predator-rich zones. In contrast, the highlands of western Pangaea preserved fossil assemblages, suggesting cooler, more temperate conditions, where vegetation shifted toward hardy conifers and seed ferns, shaping herbivore populations adapted to nutrient-poor soils and seasonal frost. Such geographic variability intensified the delicate balance of survival, creating ecosystems finely tuned to regional stability, yet vulnerable to disruption on continental scales. Even the atmosphere of this era, reconstructed from paleosol carbonates and leaf stomatal density studies, reveals a world already strained by elevated greenhouse gas concentrations long before the first eruption of the catastrophic camp event. CO2 levels estimated between 1,500 and 2,500 parts per million sustained global warmth, but also contributed to extended drought cycles and amplified monsoonal extremes, creating climatic volatility that left plants and animals in constant negotiation with shifting environmental boundaries. Variations in stomatal indices among fossil ginkgophytes and Bennettitalaean leaves show rapid fluctuations in atmospheric composition, hinting at episodic outgassing events or regional environmental stress that preceded the more dramatic volcanic episodes soon to come. These atmospheric conditions set the stage for a precarious planetary equilibrium, where life continued to flourish, but only so long as the forces beneath the crust remained dormant. Amid this rich tapestry of species, climates, and interconnected ecosystems, the late Triassic world stood as a testament to evolutionary resilience and ecological complexity. Yet every geological and biological indicator suggests that the balance was already beginning to waver. Sedimentary layers chronicled cycles of stress that only narrowly avoided tipping points. Fossil assemblages captured species operating at the upper limits of environmental tolerance. And atmospheric reconstructions described a planet pushed toward extremes by natural variability alone. All around Pangaea, subtle signs of instability accumulated quietly, unnoticed by the creatures who depended on the continuity of these habitats, yet unmistakable to modern scientists who trace each clue to the threshold of a far greater upheaval. As the final calm of the Triassic settled across the supercontinent, the deep earth stirred beneath its vast terrain, awakening forces that would soon rupture the crust, ignite unprecedented volcanic fury, and begin unraveling the fragile tapestry of life that had persisted for millions of years. The supercontinent under strain, internal pressures build. Deep within the mantle, long before the surface sensed even a tremor, thermal upwellings began to concentrate beneath Pangaea's enormous weight, driving slow but profound rearrangements in the convection cells that powered Earth's internal engine. Geophysical reconstructions suggest that the supercontinent's size disrupted normal mantle circulation, forcing heat to accumulate under its central mass instead of dispersing along oceanic boundaries. This buildup created temperature anomalies estimated to exceed surrounding regions by tens of degrees Celsius, a difference significant enough to expand underlying rock volumes and change the buoyant behavior of the lower lithosphere. Modern studies of continents riding over mantle plumes reveal comparable swelling and doming patterns, indicating that Pangaea's interior was already being primed for geodynamic instability. Throughout the heart of the supercontinent, the lithosphere responded to this subterranean heat by warping, thinning, and accumulating microscopic strains that geologists today detect in ancient fault geometries. Tectonic modeling of late Triassic plates reveals that Pangaea's crust experienced uneven mechanical stress, producing subtle but widespread deformation across more than 8 million square kilometers. Thin section analyses from present-day equivalents of Triassic rift basins show early microfaults, tiny shear zones, only millimeters in width, that betray the first stages of continental stretching. These microstructures, often invisible without magnification, provide some of the clearest evidence that the continent was quietly beginning to tear itself apart from within. Far below the continental crust, seismic tomography reveals zones of anomalously hot mantle material rising in slow but unstoppable plumes that would eventually feed some of the largest volcanic eruptions in Earth's history. While the Triassic mantle cannot be imaged directly, researchers use modern hotspots, such as Hawaii, Iceland, and Réunion, as analogues to infer the thermal and chemical properties of these ancient upwellings. Such plumes deliver massive quantities of basaltic melt toward the lithosphere, pressurizing the underside of the crust and accelerating its mechanical fatigue. Geochemical signatures in camp basalts indicate deep mantle sources rich in incompatible elements, confirming that mantle plumes were already active long before the first surface eruptions began. As these plumes pressed upward, the rigid crust of Pangaea began to arch and buckle, forming the earliest proto-rift structures identifiable in late Triassic basalt intrusions that now lie preserved across 4 continents. Structural mapping of regions in modern Morocco, eastern North America, and southwestern Europe reveals linear intrusive bodies, dikes aligned in parallel sets that reflect organized regional tension. These dikes, ranging from meters to tens of meters in width, record the directions in which the crust began to stretch as Pangaea experienced mechanical failure. Their orientations are consistent with a future tier between what would eventually become Africa, Europe, and the Americas. Within these stretching regions, mineral grains aligned along new stress paths, capturing in their orientations the earliest signatures of the tectonic violence that would follow. Electron backscatter diffraction analyses show that quartz, feldspar, and pyroxene crystals within Triassic rocks developed preferred orientations indicative of sustained directional strain. Such petrofabric evidence reveals not only the direction of tectonic pull, but also the stress magnitude, which increased steadily as heat continued to accumulate beneath the continental interior. These minute alignments function as geological seismographs, preserving snapshots of stress long before surface rupture began. Threading through the future spine of the central Atlantic, magma intruded into crustal weaknesses, forming vast dike swarms that extended for hundreds of kilometers and foreshadowed the massive volcanism still to come. Radiometric dating of these intrusions places many of them several 100,000 years before the main phase of eruptions, suggesting that magma had been silently working its way upward through the crust well before the catastrophic pulse at 202 million years ago. Many dikes are geochemically linked, demonstrating that they originated from a common deep source and infiltrated the crust along pre-existing zones of weakness repeatedly. These events mark the earliest recognizable stage of the volcanic system that would eventually devastate the planet. In sedimentary basins bordering these developing rifts, subtle shifts in deposition patterns signal episodes of uplift and subsidence driven by deep earth distortions. The Newark, Fundy, and Argena basins, once lakes and floodplains along the supercontinent's interior margins, record asymmetrical sediment layers that tilt toward extensional faults. Such tilting indicates that the crust flexed downward as magma pooled beneath it, and fault blocks began to detach along listric plains. Paleomagnetic measurements from these basins also show slight but measurable changes in Earth's magnetic inclination, suggesting tectonically driven shifts in local crustal orientation during the lead-up to breakup. At the continental margins, compressional forces created thrust belts and fault systems that recorded the mechanical strain spreading outward from Pangaea's core. Rocks in regions that are now Western Europe and northwestern Africa show evidence of far-field compression, including tight folds and reverse faults that formed as stress radiated away from the central rift axis. These structures mirror patterns seen in modern continental breakup systems, demonstrating that Pangaea's instability generated transcontinental stress fields that propagated for thousands of kilometers. Their presence confirms that the entire supercontinent, not just its interior, was being reshaped by deep Earth forces. Even the planet's magnetic field, preserved evidence of instability as magnetic minerals in cooling rocks, captured erratic pole movements associated with lithospheric reconfiguration. Magnetostratigraphic sequences from late Triassic basins record rapid shifts in magnetic inclination and declination that correlate with episodes of tectonic tilting and uplift. These changes, though subtle, reflect oscillations in Earth's magnetic field geometry caused by mantle convection reorganizing beneath the supercontinent. Variations in magnetic polarity intervals during this time correspond closely with pulses of rift-related activity, reinforcing the link between big interior changes and crustal response. By the latest Triassic, the cumulative effect of millions of years of thermal and mechanical stress had pushed the supercontinent to the brink of structural failure, leaving its crust stretched thin and its mantle reservoirs swollen with pressurized melt. Geological timelines suggest that uplift rates accelerated in the final million years before rupture, accompanied by heightened fracturing in regions that would soon split into separate landmasses. New dike intrusions, some spanning over 1,000 kilometers in length, carved fresh pathways toward the surface as the lithosphere neared its elastic limits. Every indicator, from mineral fabrics to basin subsidence patterns, points to an Earth rapidly approaching a breaking point. In the final moments before rupture, magma chambers swelled beneath the crust, fracturing overlying rock layers and building pressure that no geological framework could safely contain. Fluid inclusion studies revealed trapped pockets of volatile rich melt, indicating that CO2 and sulfur gases accumulated in large quantities within these chambers. Such gases lower magma viscosity and increase buoyancy, meaning that the combination of heat, pressure, and volatile loading made explosive ascent increasingly likely. Geophysical analogues show that systems under this level of stress cannot remain stable for long, and the Triassic Earth was no exception. As this internal strain approached its limits, the Earth's deep forces prepared to break through the surface, pushing the world toward the first cracks that would initiate Earth's deadliest hour, even as the late Triassic landscapes above remained unaware of the catastrophic transformation about to erupt from below. In this rising tension lies the final quiet before the continental shell gives way, marking the moment when subterranean pressure will transcend its hidden realm and rewrite the biosphere in a single geological instant. When the crust split open, the initial magmatic pulses, from the first breaches in the continental crust, molten rock surged toward the surface along newly formed conduits, heralding the birth of the Central Atlantic magmatic province, in a dramatic unfolding that would reshape the Triassic world. These first intrusions, imperceptible to life above, carried magma from deep mantle plumes into zones of weakness, exploiting fractures created by the tectonic stresses of the previous epoch. The dikes penetrated kilometers of lithosphere in a near-simultaneous eruption sequence, their paths guided by pre-existing faults and fractures that crisscrossed the supercontinent's interior. Radiometric dating of zircon crystals preserved within these intrusions indicates that the pulses occurred within mere hundreds of thousands of years, a geologically brief interval signaling the onset of planetary-scale volcanism. In the early stages, basaltic dikes penetrated kilometers of lithosphere, creating a network of intrusions stretching across what would become 4 modern continents. From North America's Newark Basin to the Argana Basin of Morocco and southwestern Europe, these intrusions followed roughly linear trajectories, reflecting the directional pull of the fracturing crust. The sheer scale of these dikes, some extending over 1,000 kilometers in length, illustrates how Pangaea's rigid crust had been primed for rupture. Modern geophysical analogues show that such linear intrusions are capable of delivering enormous volumes of magma to to the surface, setting the stage for subsequent flood basalt flows that would blanket vast regions. Gas-rich magma, loaded with CO2 and sulfur, began to accumulate in shallow chambers, pressurizing the overlying rock until it could no longer contain the swelling melt. Petrological analyses of early camp basalts reveal vesicle patterns indicative of rapid gas expansion, suggesting that even at the first pulses, degassing was extensive. The pressure exerted by these volatile-laden magmas fractured overlying rock layers, creating conduits for eruptions and releasing chemically charged gases into the atmosphere. Although modest compared with the later flood basalts, these first degassing events marked the opening of a feedback loop where magmatic pressure and crustal weakness interacted to accelerate eruption dynamics. Radiometric dating of these initial intrusions confirms their emplacement occurred almost simultaneously across vast regions, marking a synchronized planetary scale event. UPB zircon ages from dikes in Morocco, North America, and Europe all cluster within a narrow window around 201-202 million years ago, providing compelling evidence for a coordinated volcanic onset. The temporal coherence of these intrusions underscores the scale of geodynamic forces at work, implying that the mantle plume feeding camp was both extensive and unusually efficient in channeling melt toward the lithosphere. This synchronization ensured that the first pulses were not isolated, but instead a continental-scale harbinger of devastation. Surface manifestations appeared first as small fissure eruptions, spattering lava onto floodplains and altering local drainage patterns in real time. Thin, linear lava flows followed the paths of the fissures, sometimes traveling tens of kilometers, and began to cover river valleys, lakes, and low-lying plains. Sedimentary layers preserved in these regions show rapid transitions from fluvial deposits to basalt flows, recording the sudden incursion of molten rock into familiar landscapes. Even small eruptions disrupted the hydrology of these systems, creating temporary dams and forcing water bodies to reroute, hinting at the profound environmental effects that would amplify with each subsequent pulse. Chemical analyses of the earliest flows reveal a mixture of tholeiitic basalts and volatile-rich magmas, hinting at complex mantle sources feeding the eruptions. Trace element ratios and isotopic compositions suggest contributions from deep mantle plumes modified by shallow lithospheric contamination. This heterogeneous chemistry produced basalts capable of higher fusion rates and significant gas release, creating the potential for both widespread lava coverage and localized explosive activity. Even at this early stage, the interplay of composition, pressure, and crustal structure defined the behavior of the eruptions, dictating which flows advanced rapidly and which stalled in ephemeral lava lakes. Sedimentary basins adjacent to these intrusions capture evidence of rapid subsidence, indicating that the lithosphere was flexing under the load of the intruding magma. In the Newark Basin, for example, clastic layers thin abruptly toward newly formed dikes, while interbedded paleosols show sudden burial events consistent with rapid lava accumulation. The weight of the intrusions depressed the crust locally, triggering small-scale earthquakes and altering groundwater circulation. These early structural adjustments foreshadowed the larger tectonomagmatic interactions that would later accompany full-scale flood basalt emplacement. Even distant regions, far from the first fissures, show magnetic anomalies consistent with the emplacement of dikes and sills tens of kilometers away. Paleomagnetic studies reveal abrupt changes in inclination and declination in lava flows and intrusions, suggesting that the early magmatic network had a far-reaching effect on crustal stress fields. These signals provide a global fingerprint of initial camp activity, confirming that the first pulses were not isolated events, but part of a continent-spanning phenomenon affecting regions that had yet to witness a single lava flow. In some areas, lava fountains rose hundreds of meters, sending pyroclasts and gas into the atmosphere and initiating the first local climatic perturbations. These fountains, fueled by volatile rich magma, injected aerosols and sulfur gases into the lower atmosphere, creating temporary regional cooling and acid precipitation. Fossilized charred plant remains in proximate sedimentary layers show evidence of stress and mortality, indicating that even the earliest eruptions had immediate ecological consequences. These first surface manifestations foreshadowed the planetary scale climatic effects that would accompany the larger camp eruptions. The progression from initial intrusions to continuous flood basalt coverage was neither uniform nor slow. Pulses of activity created a patchwork of eruptions across the supercontinent. Some fissures fed long lava flows, while others stalled as magma pooled underground, forming sills and laccoliths that redistributed heat and stress within the crust. The episodic nature of these early eruptions indicates that the supercontinent was entering a period of rhythmic but accelerating instability, each pulse nudging the crust closer to catastrophic failure. These earliest pulses transformed the landscape in hours to days, carving new topography, damming rivers, and disrupting established ecosystems, while signaling the onset of an unprecedented magmatic epoch. Fossil records reveal that local fauna and flora experienced sudden habitat alteration, illustrating how quickly the geological upheaval translated into ecological consequences. As lava and gas reached the surface, Pangaea's first tangible step toward the deadliest hour in its history had begun, a process both sudden and inevitable. With each surge through subterranean channels, the Earth began to move beyond hidden stress into visible eruption, hinting at the global-scale environmental catastrophe that would follow these initial fractures. The interplay of crustal rupture, intruding magma, and atmospheric degassing set the stage for the full-scale flood basalts of Camp, ensuring that life on the surface would soon confront forces capable of reshaping the planet's climate, landscapes, and ecosystems in a single geologic instant. The Great Eruption, Camp's lava floods, ignite the crisis. Flood basalts began pouring across lowlands, consuming rivers and swallowing valleys beneath sheets of molten rock. The scale of these flows was unprecedented, rapidly transforming familiar landscapes into a fiery, unrecognizable terrain. From fissure sources that had formed in the prior stage of tectonic stress, lava advanced in sheets tens of meters thick, obliterating existing ecosystems and burying sediments that had persisted for millions of years. Even the most resilient plants and animals had little chance to escape the advancing floods, and the first tangible evidence of Camp's catastrophic potential was etched into the land itself. From present-day North America to Morocco and Europe, the Earth's crust groaned under the weight of unprecedented lava volumes. These lava sheets, produced by massive magma chambers beneath Pangaea, spread laterally for tens of kilometers, converging to create continuous blankets across vast regions. The stress of the accumulating molten rock caused subtle flexing and warping of the crust, which in turn influenced the direction and thickness of successive flows. In sedimentary basins bordering the new basalt fields, paleosol layers record abrupt burial events, revealing how quickly environments were altered by these unstoppable rivers of fire. Flow after flow stacked upon each other, producing thick blankets of basalt that would insulate the land for millennia to come. Cooling processes were dramatic, with thick flows forming columnar jointing that preserved precise information about flow thickness, cooling rate, and eruption duration. These early flood basalts were already altering local climates by radiating intense heat and initiating small-scale greenhouse effects. Fossil evidence shows that charred plant material and thermally stressed organisms were trapped between layers, providing a stark record of immediate ecological consequences. Paleogeographic reconstructions show that lava traveled tens of kilometers from its source fissures, damming lakes and altering drainage on a continental scale. Streams and rivers were abruptly obstructed, creating temporary lakes and forcing sediment redistribution. Sedimentary records reveal rapid transitions from fluvial to volcanic deposition, often within a few years. These hydrological disruptions were among the first signs that the full environmental impact of camp would extend far beyond the immediate zones of lava flow. Gas emissions intensified as surface lava flows expanded, releasing sulfur dioxide, carbon dioxide, and other volatiles into the atmosphere. Early degassing already began altering air composition locally, increasing acidity in precipitation and creating regional temperature anomalies. These gases, though initially confined, foreshadowed the global-scale atmospheric effects that would soon drive mass extinctions. Modern geochemical analyses of ancient basalts indicate that the first pulses of camp were responsible for significant emissions that rivaled any prior volcanic event of the late Triassic. Cooling basalts preserved distinct columnar jointing, revealing the rates at which enormous lava sheets solidified in the open air. These natural geometric patterns, visible across thousands of kilometers of preserved rock, serve as a direct archive of eruption intensity and thermal history. The presence of multiple stacked flows demonstrates how rapidly and repeatedly Pangaea's crust was resurfaced, providing a geological record of pulse-driven episodic volcanism. Each layer tells a story of molten rivers freezing into an unyielding new landscape. Fossilized plant debris buried in interlayered sediments testifies to the immediacy of ecosystem destruction along flow margins. Evidence of scorched vegetation and sudden mortality highlights the suddenness of the lava advance. Even animals capable of rapid migration would have struggled to evade these advancing basalts, and localized extinctions became embedded in the fossil record. These early losses foreshadowed the more extensive biological crises that would follow as camp continued to pour lava across continental expanses. The repetitive pulsing of lava eruptions over hundreds of kilometers created a patchwork of newly formed topography, with plateaus and ridges rising from the scorched surface. Differential flow thickness and eruption intensity molded the land into a rugged, uneven terrain. Geophysical modeling shows that these changes altered drainage networks and imposed additional mechanical stress on adjacent lithospheric blocks. The landscape, once dominated by rivers and forests, now bore the scars of repeated, unstoppable volcanic activity. Temperature reconstructions from paleosols indicate localized warming, showing that the land itself became inhospitable to most terrestrial life within weeks of the first flows. Thermal stress in soils and near-surface environments likely exceeded 50-60 degrees Celsius in some regions, making survival impossible for even heat-tolerant organisms. Fossilized insects and small vertebrates preserved near flow margins suggest rapid heat shock and mortality, highlighting the immediacy of camp's lethal effects. The land, burning under successive lava sheets, provided only a fleeting window for life to adapt or escape. Volcanic gases mix with ash and aerosols, beginning the atmospheric transformations that would later trigger a global environmental crisis. Sulfur aerosols and fine particulates entered the lower atmosphere, initiating acid rain events and scattering sunlight regionally. The first pulses set off a chain reaction. Lava-induced heating increased gas emissions, which in turn altered climate and weather patterns. Even at this early stage, Camp's eruptions demonstrated the potential to influence global systems far beyond the immediate lava fields. Even in regions distant from the main lava flows, sedimentary layers record acid rain, soot deposition, and early signs of airborne ecological stress. Palynological records indicate declines in plant diversity, while geochemical proxies show elevated levels of sulfuric compounds and carbon dioxide. The ecological consequences were no longer local. The earliest signs of atmospheric perturbation now stretched across entire continental margins, hinting at the planetary scale environmental impact that would follow. Molten rivers and burning landscapes stretched relentlessly, yet the unseen atmospheric changes promised a more insidious, far-reaching threat to life on Pangaea. The land itself was engulfed in fire, but the true killer lay in the transformation of the air above. Sulfuric acid aerosols, carbon dioxide buildup, and heat-trapping gases began a cascade of environmental change that would gradually suffocate ecosystems, alter the climate, and drive extinction on a global scale. The stage was set, the great eruption had begun, and while lava reshaped the continents, the atmosphere prepared to deliver its lethal judgment. Air in revolt. Sudden atmospheric toxification. Sulfur dioxide and carbon dioxide poured into the sky, forming dense clouds that trapped heat and altered weather patterns across continents. The once clear atmosphere became a complex chemical theatre where greenhouse gases, aerosols, and volcanic halogens began to interact in unpredictable ways. The land below was already scarred by lava flows, yet the air above was poised to impose an even more insidious form of devastation. Within weeks, regions downwind of camp eruptions experienced temperature swings and acidic precipitation, invisible yet lethal to both terrestrial and freshwater life. Aerosol particles from eruptive pulses reflected sunlight, creating sudden regional cooling events that juxtaposed the heat radiating from lava fields below. This duality, intense surface heating and atmospheric shading, produced chaotic weather patterns. Paleoclimate reconstructions reveal rapid oscillations between heat waves and cold snaps, each shift exerting stress on plant communities and animal populations. Evidence from sedimentary layers shows deposition of fine volcanic ash and sulfate-rich dust, marking the movement of toxic clouds across previously stable ecosystems. Ozone concentrations fluctuated unpredictably, with volcanic halogens and radicals catalyzing rapid chemical reactions that thinned protective layers of the atmosphere. Increased UV exposure, though invisible to the naked eye, likely compromised plant photosynthesis and induced mutations in sensitive organisms. Fossilized plant cuticles suggest elevated UV stress through changes in pigmentation and stomatal density, capturing the direct biological consequences of atmospheric chemical upheaval. This invisible assault added another layer of strain atop the already devastated landscapes below. Wind patterns redistributed toxic gases, spreading acid rain hundreds of kilometers from eruption sites and disrupting terrestrial and freshwater ecosystems alike. Paleosols record rapid pH shifts, indicating that soils became inhospitable almost overnight in some areas. Freshwater lakes, once sources of stability for regional life, turned acidic and oxygen depleted, killing fish and invertebrates en masse. The atmosphere, once a buffer for life, became a conveyor of destruction, capable of impacting regions far removed from the initial eruptions. Buried in layers of sediment, proxies from peat and lake deposits reveal abrupt pH shifts, capturing the immediate acidification of soils and waters in proximity to camp flows. This chemical stress is mirrored in paleobotanical evidence. Fern spores and other sensitive taxa exhibit dramatic declines, reflecting the rapid collapse of vegetative networks that sustained herbivorous and omnivorous species. These early acidification events set the stage for cascading ecological failures, linking atmospheric chemistry to biosphere-wide vulnerability. Paleotemperature reconstructions show oscillations of warming and cooling, a volatile response to greenhouse gas pulses and aerosol shading working in tandem. Measurements derived from isotopic analyses of carbonate nodules indicate fluctuations of several degrees Celsius over remarkably short timescales. These abrupt climatic swings would have been impossible for many organisms to track or adapt to, amplifying the mortality already induced by lava inundation. Life faced a dual challenge, surviving the fiery flows below and the chemically unstable skies above. Fossilized flora exhibits rapid physiological stress, including leaf deformation and abrupt shifts in stomatal density, recording the atmospheric assault on photosynthesis. These morphological changes offer direct evidence of environmental toxicity and provide a window into the cascading effects of atmospheric perturbation on primary productivity. Declines in photosynthetic efficiency would reverberate up the food chain, weakening herbivore populations and destabilizing predator-prey dynamics within already stressed ecosystems. Carbon isotopic anomalies in soil and sediment layers indicate massive CO2 injection that destabilized carbon cycles and signaled a planet-wide chemical imbalance. Elevated atmospheric CO2, coupled with reduced ozone and episodic cooling, produced a climate both hot and erratic. Geochemical analyses of organic and inorganic carbon fractions demonstrate rapid excursions that prelude larger-scale greenhouse effects. The planet's atmospheric chemistry had shifted irreversibly, laying the foundation for long-term ecological collapse. Atmospheric opacity increased, scattering sunlight and lowering regional visibility, a phenomenon captured indirectly in sediment color changes and preserved plant remains. This diffuse shading reduced photosynthetically active radiation, further stressing plants already grappling with acid rain and temperature swings. Contemporaneous insect fossils suggest developmental abnormalities consistent with environmental stress, highlighting the wide-ranging biological impact of atmospheric toxification. Poured from darkened skies, sulfuric acid rain scoured surfaces, chemically eroded soil profiles, and altered the chemical composition of freshwater habitats. The combined effect of direct acid deposition and aerosol-induced UV stress created lethal conditions for many species, particularly amphibians, freshwater invertebrates, and shallow-rooted plants. The planet's air had shifted from a life-sustaining medium into a vector of systemic crisis, foreshadowing the broader environmental calamity that would define the end Triassic. Even distant regions, once considered insulated, began to record climatic and chemical perturbations, demonstrating the far-reaching scale of volcanic atmospheric influence. Sedimentary and paleosol evidence shows synchronous stress events across hundreds of kilometers, indicating that the camp eruption's impact was global rather than localized. Life everywhere, from equatorial forests to mid-latitude floodplains, now contended with chemically hostile air that had previously been a stable environmental foundation. Through every corner of the continents, the poisoned air wove a lethal web that reached far beyond the scorched land, infiltrating forests, rivers, and freshwater basins alike. Sulfate aerosols, carbon dioxide, and acid rain combined to stress ecosystems on a scale previously unseen, leaving life struggling to cope with sudden chemical and thermal extremes. Vegetation weakened, herbivores faltered, and predators confronted a collapsing food chain, while subtle signals in sediments hinted at the ocean's impending suffocation. Invisible yet pervasive, the atmosphere had become a silent arbiter of survival, transforming from a protective envelope into a global agent of mortality. In this escalating crisis, the land had burned and the air had turned toxic, and now the seas were preparing to reveal the next chapter of Earth's deadliest hour. Seas without breath, the collapse of marine oxygen. Oxygen levels in shallow seas plummeted first, choking reefs, lagoons, and coastal habitats in a subtle yet relentless suffocation. Coral frameworks that had persisted for millions of years began to crumble as sessile invertebrates perished, leaving skeletal structures bleached and fragile. Lagoonal fish populations vanished almost entirely, while bivalves and gastropods show mass mortality in fossil assemblages, capturing the first harbingers of oceanic collapse. Sedimentary deposits record these losses through sudden concentrations of disarticulated shells, a silent chronicle of life abandoned by the waters around it. Deeper waters, insulated from surface turbulence, began to stagnate, allowing hydrogen sulfide and other toxic compounds to accumulate in darkened basins. These inhospitable depths became chemical traps, where any oxygen entering the system was rapidly consumed by decomposition and microbial activity. Geochemical signatures in carbonate sediments reveal elevated sulfur and iron concentrations, confirming the widespread onset of euxinic conditions, lethal not only to fish but to plankton and benthic communities alike. Even the most resilient organisms could not escape this creeping, invisible threat. Geochemical signatures in carbonate rocks record sudden drops in redox-sensitive elements, revealing anoxic conditions that spread across entire continental shelves. Molybdenum, uranium, and vanadium concentrations shift abruptly in sediment cores, providing a precise timeline of oxygen depletion. Laminated sediment layers, devoid of biotubation, document the collapse of benthic ecosystems, while fossilized burrows become rare or absent altogether. These chemical and sedimentary markers allow scientists to reconstruct the staggering speed and scale of the marine die-offs that ensued. Ammonoids, bivalves, and other marine invertebrates show abrupt mortality in fossil assemblages, capturing the first pulses of oceanic die-off. Cephalopods with delicate shells often appear in dense, monospecific beds, indicating mass mortality events rather than gradual decline. Bivalve species, once abundant across shelves, disappeared, leaving gaps in the food web that would ripple through marine ecosystems for millennia. The fossil record thus serves as both a warning and a testament to the ocean's fragility in the face of chemical upheaval. Marine plankton populations, crucial to carbon cycling, collapsed under oxygen stress, altering nutrient flows and destabilizing global productivity. Calcareous nanoplankton show sharp reductions in abundance, as indicated by microfossil assemblages in deep-sea cores. Phytoplankton decline reduced primary productivity, cascading up the food chain to herbivorous zooplankton and small fish, further amplifying the ecological domino effect. The ocean's capacity to sequester carbon weakened, accelerating atmospheric CO2 accumulation and linking marine collapse to global climate perturbations. Traces in sulfur isotopes reveal widespread hydrogen sulfide upwelling, poisoning shallow waters and creating lethal conditions for vertebrate and invertebrate species alike. Fossil fish exhibit signs of gill damage consistent with chemical toxicity, while sediment cores reveal sulfur enrichment coincident with widespread extinction horizons. These pulses of toxic upwelling were episodic, yet each successive event left fewer survivors and more chemical instability, compounding the ocean's decline and intensifying ecological stress on an unprecedented scale. In the calm, laminated strata of ancient basins, sediment cores reveal laminated layers with few burrowing organisms, indicating that benthic ecosystems were decimated across broad regions. Microbial mats proliferated in the absence of larger fauna, further altering sediment composition and geochemistry. Trace element ratios and isotopic anomalies suggest that these microbial communities were fueled by decomposing organic matter, feeding on the remnants of once thriving ecosystems. The ocean floor had become a shadow of its former vibrancy, a chemical graveyard echoing the violence unfolding above. Rapid ocean warming amplified stratification, preventing replenishment of oxygen from the surface and accelerating anoxic expansion. Surface waters, heated by greenhouse gases and reduced circulation, no longer mix efficiently with deeper layers, isolating oxygen-rich zones from nutrient-depleted depths. This thermal barrier intensified stress on mid-water and deep-sea organisms, while shallow seas faced alternating pulses of heat and chemical toxicity. The oceans had become a layered death trap, with each stratum exhibiting unique but deadly conditions. Evidence from trace metals and rare earth elements demonstrates that these anoxic events were episodic, yet cumulative, each pulse more severe than the last. Molybdenum and vanadium concentrations spike repeatedly in sedimentary sequences, marking successive pulses of oxygen depletion that left increasingly barren habitats. Fossil assemblages show corresponding pulses of mortality, suggesting that life had no time to adapt between events. This pattern underscores the rapidity with which Earth's marine systems were pushed beyond resilience during the Triassic Collapse. The collapse of oceanic life began to feed back on atmospheric chemistry, releasing CO2 and methane from decaying biomass and exacerbating global warming. Dead marine organisms sank, decomposing anaerobically and liberating gases that further altered climate and ocean chemistry. These feedback loops created a vicious cycle. Oxygen depletion promoted death, death released gases, and gases intensified warming, which in turn worsened oxygen stratification. The ocean's collapse was no longer isolated, it reverberated throughout the entire planetary system. Even isolated deep basins were not spared, showing that no corner of the oceans remained immune to suffocation. Fossil records from the Tethys, Panthalassa, and marginal basins all exhibit signs of oxygen stress, demonstrating the global reach of these events. Life everywhere was constrained to shrinking refugia, and even these pockets would soon be tested by chemical toxicity, temperature extremes, and nutrient imbalances. The oceans had become a planet-wide deathscape, a forewarning of ecological dominoes about to fall on land. Continental landscapes felt the pull of collapsing oceans. Oxygen-starved waters encroached on continental shelves, and signals of cascading ecological collapse began to echo back onto terrestrial habitats, linking oceanic and land crises. The poisoning of rivers and estuaries, coupled with climate feedbacks from dying oceans, stressed coastal and inland ecosystems, leaving land, plants, and animals increasingly vulnerable. Marine die-offs were not an isolated tragedy, they were a planetary signal that the Triassic world had entered its deadliest hour. In this interconnected collapse, the fate of the seas foreshadowed the suffering soon to grip life on the continents, continuing the inexorable march of Earth's deadliest hour. Land in turmoil, temperature shocks, and climate whiplash. In the heart of Pangaea, scorched soils cracked under unrelenting heat, exposing root systems of plants that had thrived for millions of years. Ferns and gymnosperms withered in place, their delicate vascular systems unable to withstand the sudden desiccation. Paleosols reveal baked horizons and calcrete accumulations, evidence of extended aridity that forced terrestrial communities to scramble for limited moisture. Even the most resilient flora displayed stress indicators in preserved leaves, including shriveled cuticles and reduced stomatal density, capturing the physiological toll of climate extremes. Flash floods, driven by erratic monsoonal surges, carved new channels through valleys and plains, uprooting vegetation and displacing animal populations. Sudden torrents overwhelmed riverbanks and lowland areas, leaving layers of sediment-scoured plains in their wake. Fossil assemblages document mass disarticulation of small vertebrates and reptiles, evidence of rapid transport and mortality events. Ancient river terraces and cross-bedded sandstones indicate that these destructive episodes alternated unpredictably with periods of severe drought, creating landscapes in constant ecological flux. Tree rings in fossilized woods reveal abrupt growth interruptions, chronicling heat waves and drought cycles far beyond the tolerance of Triassic flora. These dendrochronological records suggest not only seasonal stress, but multi-year extremes that stunted growth and triggered mortality across generations. The disruption of plant communities had cascading effects. Herbivores dependent on leaves, seeds, and stems found little sustenance, triggering starvation events that rippled through food webs. Pollen assemblages confirm a decline in diversity, reflecting the collapse of plant populations once considered stable and widespread. Lakes and rivers alternated between desiccation and sudden inundation, creating lethal swings in freshwater availability for amphibians, reptiles, and early synapsids. Fossil amphibians display size reductions and skeletal deformities consistent with prolonged water stress, while sedimentary evidence points to repeated subaerial exposure followed by rapid sediment deposition during flash floods. This hydrological whiplash prevented long-term adaptation, making survival a matter of chance. The juxtaposition of drought and deluge became a defining feature of Pangaea's destabilized landscapes. Trace fossils indicate frantic migration patterns, as herbivorous species sought limited grazing grounds only to encounter barren or poisoned landscapes. Trackways show abrupt directional changes and dense clusters of footprints abruptly ending, suggesting mass die-offs or sudden environmental barriers. These behavioral imprints highlight the desperate struggle of terrestrial animals to find food and water in a world where previous migration routes had been rendered unviable. Predators, following these prey populations, confronted starvation and habitat fragmentation, intensifying stress throughout the ecosystem. Layers of ancient dust reveal repeated episodes of soil erosion and dust storms, blanketing plant communities and reducing photosynthetic efficiency. Wind-driven deposits, preserved as loess layers, capture the scale of aridification and ecological disruption. Dust accumulation hindered the growth of understory plants and suffocated small vertebrates, while nutrient cycles were disrupted as topsoil was stripped from vulnerable landscapes. These processes exacerbated existing climatic stress, producing a feedback loop that reinforced environmental extremes. Volcanic CO2 pulses, combined with methane release from warming soils, amplified temperature fluctuations and drove local climates into extremes of heat and humidity. Paleoclimate reconstructions suggest that regional warming reached levels intolerable to many terrestrial species, with some areas experiencing heat stress beyond the limits of metabolic tolerance. Isotopic analyses of carbonate nodules in soils corroborate rapid greenhouse gas accumulation, linking atmospheric chemistry directly to the swings in temperature and precipitation observed across Pangaea. The terrestrial climate was no longer merely variable, it had become erratic and uninhabitable in places. Fossilized eggs and juvenile skeletons suggest that reproductive failure became widespread as young animals perished under sudden heat stress, or habitat loss. High juvenile mortality rates are evident across archosaurs, synapsids, and early dinosaur forms, revealing that population replenishment had slowed to a dangerous degree. Nesting sites show evidence of scorching, flooding, or abandonment, reflecting how extreme weather events disrupted critical life history stages. The inability of young to survive portended population collapses that would echo for generations. Isotopic signatures in paleosols record rapid swings in precipitation and temperature, confirming that climate instability was both abrupt and globally pervasive. Variations in oxygen and carbon isotopes illustrate repeated cycles of wet-dry and heat-cold extremes that stressed both flora and fauna. Such oscillations created patchy, habitable zones, fragmenting ecosystems into isolated refugia. Plants and animals that had previously thrived in contiguous landscapes now faced unpredictable microclimates, where survival demanded either mobility or extraordinary resilience. Predators, already stressed by dwindling prey, faced escalating challenges as ecosystems fractured and resource competition intensified. Fossil evidence suggests elevated stress markers in theropod teeth and limb bones, reflecting both malnutrition and increased intraspecific conflict. Carnivores became trapped in a web of scarcity, with mortality spikes corresponding closely to periods of climate shock. The disruption of trophic hierarchies illustrates how environmental volatility cascaded through every ecological layer, magnifying the consequences of climate extremes. Even the hardiest desert-adapted species experienced mortality peaks, demonstrating that no terrestrial refuge remained entirely safe. Fossilized remains in arid basins reveal episodic die-offs despite adaptations to heat and low water availability. Extreme conditions exceeded evolutionary tolerances, highlighting that the Triassic world had entered a phase of environmental stress unprecedented in both magnitude and speed. Survival depended not only on adaptation but on chance, and many species failed to meet this brutal test. Life clung precariously to a destabilized landscape. Pangaea's dominant animals teetered on the brink, signaling the next wave of catastrophic extinctions. Widespread climate whiplash, habitat fragmentation, and reproductive failure combined to produce population collapses even among apex species. As plants withered, rivers desiccated, and storms raged, terrestrial life faced its most severe trial yet. In the wake of oceanic anoxia and atmospheric poisoning, the land itself now mirrored the volatility of a dying planet, setting the stage for the imminent die-off of Earth's most familiar and dominant Triassic inhabitants. The fall of giants. Archosaur dominance crumbles. In the riverine corridors once ruled by massive phytosaurs, skeletal remains now tell a story of starvation and shrinking populations. Bones display growth arrest lines and fragile cortical structures, indicators of prolonged malnutrition as prey became scarce and rivers alternated between drought and flood. Fossil assemblages suggest a precipitous decline in adult numbers, while juveniles rarely survive to maturity. Phytosaurs, once apex aquatic predators, found themselves unable to adapt quickly enough to the rapidly changing Triassic landscapes, and their decline rippled across the ecosystems that depended on their predatory regulation. Aetosaurs, armored sentinels of floodplains, vanished from the fossil record in pulses that mirror climatic extremes and dwindling vegetation. Their herbivorous diet relied on ferns, cycads, and seed plants that suffered under recurrent heat waves and desiccation. Sediment cores from late Triassic basins reveal abrupt interruptions in palynological abundance, correlating with the disappearance of aetosaurs in specific regions. Even the protective osteoderms that had shielded these creatures from predators could not protect them from systemic starvation and habitat collapse. Rauisuchians, apex predators whose bite shaped entire ecosystems, display pathologies consistent with nutritional stress and competitive collapse. Skeletal examinations reveal healed fractures, dental wear anomalies, and evidence of bone remodeling suggestive of chronic malnutrition. As herbivores declined, these top predators encountered dwindling prey availability, forcing them into desperate scavenging behaviors. Their ecological dominance eroded, leaving formerly unchallenged niches vulnerable to smaller, more adaptable competitors. Juvenile skeletons of archosaurs indicate catastrophic reproductive failure, with nests abandoned or flooded during sudden storms. Preservation of eggs in sedimentary layers shows either crushing or complete destruction, highlighting the lethal effects of flash floods and rapid environmental shifts. Growth ring analyses on juvenile bones reveal stunted development and metabolic stress, painting a stark picture of species struggling to propagate under extreme environmental volatility. Reproductive bottlenecks accelerated population collapse, ensuring that losses could not be compensated in subsequent generations. Dental microwear patterns reveal shifting diets and desperate foraging attempts as prey populations collapsed. Predators exhibited abrasive tooth wear from consuming tougher or less nutritious food, while omnivorous archosaurs expanded their diets opportunistically. The paleobiological record captures a desperate scramble for survival, with physiological strain escalating as environmental conditions fluctuated unpredictably. Dietary stress amplified mortality rates, contributing to a cascading breakdown of terrestrial food webs. Encased in mineralized feces, coprolites reveal the hidden story of failed predation, showing apex archosaurs increasingly consuming indigestible or toxic matter as prey became scarce. Analyses of these preserved droppings indicate that top predators ingested plant matter, bones, and even the shells of small armored animals, demonstrating extreme dietary stress. Geochemical assays show elevated levels of heavy metals and unusual isotopic ratios, suggesting that these desperate feeding behaviors may have contributed to physiological stress or poisoning. Such evidence adds a layer of behavioral insight, revealing how apex species were forced into maladaptive strategies as their ecological niches collapsed. The patterns recorded in coprolites correspond temporally with skeletal pathologies and trackway gaps, reinforcing the picture of a population struggling to survive under rapidly deteriorating conditions. Trace fossils, including trackways and feeding marks, show abrupt cessations in movement across once bustling landscapes. Paths that once indicated migration, hunting, or social congregation suddenly vanish, leaving gaps that align with extinction pulses documented in skeletal remains. These behavioral snapshots highlight the immediate consequences of habitat fragmentation, reduced prey availability, and environmental unpredictability, emphasizing the speed at which apex species could be eliminated from entire regions. Sedimentary evidence aligns extinction pulses with climate whiplash, linking habitat loss directly to apex mortality. Layers of sand, silt, and volcanic ash preserve repeated episodes of drought, flood, and sedimentation that correspond with the decline of dominant archosaur populations. These environmental stressors did not act in isolation. They compounded each other, creating landscapes incapable of sustaining complex trophic structures. The geology itself becomes a silent record of ecological collapse, etched in strata across Pangaea. Isotopic analyses of bones suggest stress-induced metabolic changes preceding mass mortality events. Shifts in oxygen and carbon isotope ratios indicate rapid fluctuations in hydration, temperature, and diet composition. Such evidence underscores the physiological limits of large Triassic vertebrates and confirms that environmental extremes, rather than disease or predation alone, were primary drivers of extinction. Apex species were particularly vulnerable because of their high energetic demands and specialized ecological roles. Comparisons across Pangaea indicate synchronous die-offs, revealing a global collapse rather than isolated regional extinctions. Fossil records from North America, Europe, and Northern Africa demonstrate simultaneous population crashes in multiple archosaur lineages. This synchronicity points to a planet-wide mechanism linking the combined effects of climate whiplash, atmospheric stress, and ecosystem destabilization to the rapid disappearance of apex taxa. The fall of giants was not a local phenomenon, it was a continental-scale event with global implications. As vegetation receded and prey vanished, competition intensified, forcing some survivors into marginal habitats or scavenging niches. Smaller, more generalist species began occupying territories previously dominated by apex predators, capitalizing on the vacated ecological space. Fossil evidence shows that early dinosauriforms, small crocodilomorphs, and other opportunists expanded in distribution, exploiting the niches left behind. In this reshuffling of ecosystems, survival depended not only on adaptability, but also on timing and fortuity, illustrating the selective pressures that would shape future vertebrate communities. Predatory hierarchies fractured, with formerly dominant species reduced to rare, struggling remnants. Isolated populations faced genetic bottlenecks and increased inbreeding, while predatory behavior shifted toward opportunistic feeding and scavenging. Ecosystem structure, once highly stratified and predictable, became chaotic and unstable, exposing the vulnerability of lineages that had previously maintained long-standing dominance. Even species with formidable anatomical adaptations could not withstand the rapid unraveling of the environmental and ecological scaffolding that supported them. Yet, amid this catastrophic decline, smaller and more adaptable species began to navigate the destabilized landscapes, foreshadowing the rise of new ecological players. Early dinosaurs, nimble archosauriforms, and generalist herbivores demonstrated resilience by exploiting patchy resources and refugia. Their emergence signals a profound shift. As the giants of the Triassic faltered, evolutionary opportunities expanded for those capable of enduring extremes. This transition lays the groundwork for a new chapter in Pangaea's history, where survivors would inherit the reshaped land and redefine the balance of power among terrestrial vertebrates. Survivors in the shadows, dinosaurs and the art of persistence. In worlds reshaped by extinction, small dinosaurs navigated landscapes littered with ecological traps and opportunities. Where the massive phytosaurs, atasaurs, and rauisuchians had once dominated, early dinosaurs and nimble archosauriforms exploited empty niches, slipping through the gaps left by extinction. Fossil evidence from North America, Europe, and Northern Africa reveals that these survivors maintained low-density populations, yet their persistence across widespread basins demonstrates remarkable ecological resilience. In a world suddenly fractured by climate whiplash, toxic air, and oxygen-depleted waters, their modest size and flexible behaviors conferred a survival advantage. Anatomical studies reveal early adaptations in limb structure, metabolism, and dentition that allowed these species to exploit a variety of food sources. Small herbivores developed efficient jaw mechanics, capable of processing both tough vegetation and opportunistic insect prey, while carnivorous forms retain teeth suited for a wide range of small prey items. Bone histology indicates elevated growth rates, suggesting metabolic strategies that balanced energy efficiency with the need for rapid development in uncertain environments. These traits collectively allowed modestly sized dinosaurs to thrive where larger, specialized archosaurs could not. Preserved in ancient sediment, the trackways demonstrate flexible movement patterns, indicating rapid dispersal across fragmented habitats. Pathways through floodplains, ephemeral lakes, and forest margins demonstrate that early dinosaurs could traverse obstacles that would have challenged heavier predators. Foot morphology suggests adaptations for sprinting, climbing, and navigating uneven terrain, reflecting an ability to exploit microhabitats. These tracks, preserved alongside environmental deposits, provide a living map of survival strategies unfolding across diverse Pangaean landscapes. Evidence of selective predation suggests that survival depended as much on cunning and timing as on raw strength. Trace fossils and tooth marks indicate that small carnivorous dinosaurs and archosauriforms focused on juvenile prey, weakened individuals, or carcasses, minimizing direct competition with each other and with emerging mid-sized predators. Opportunistic feeding behaviors demonstrate ecological intelligence, showing how survival often relied on exploiting transient resources rather than brute force. Behavioral flexibility became a critical determinant of persistence in an ecosystem still reeling from collapse. Small herbivorous archosaurs utilized microhabitats and marginal vegetation, avoiding competition and predation from larger survivors. Fossil plant assemblages suggest these animals foraged among ferns, horsetails, and early conifers, growing in nutrient-poor soils or marginal zones unsuitable for larger species. By concentrating on overlooked niches, these dinosaurs avoided the pressures that had decimated giants, establishing a foothold that allowed populations to persist despite extreme environmental fluctuations. Jaw mechanics and dental wear patterns revealed diets that could shift between insects, small vertebrates, and plant matter depending on availability. Analysis of microwear and isotopic signatures shows remarkable dietary plasticity, a trait critical for survival in ecosystems experiencing rapid climate swings, oxygen stress, and habitat fragmentation. Fossilized fecal matter corroborates this evidence, demonstrating omnivorous and opportunistic feeding strategies that kept populations viable when conventional food sources were scarce. Isotopic signatures, preserved in fossils, reveal metabolic flexibility, suggesting that these dinosaurs could withstand fluctuating temperatures and variable water sources. Oxygen isotope ratios in bones suggest rapid adjustments to seasonal extremes, while carbon isotopes indicate the ability to utilize diverse plant and animal resources. These physiological traits allowed small dinosaurs to maintain homeostasis, reproduce, and forage across ecologically heterogeneous landscapes, even as climatic instability intensified. Nest placement and reproductive strategies appear optimized for rapid turnover in unstable environments, ensuring some offspring survived extreme conditions. Fossilized nests, often placed on raised substrates or in sheltered microenvironments, reveal clutch sizes tailored for maximum survival. Growth rings in juvenile bones suggest staggered hatching and accelerated development, enabling rapid population replenishment and resilience in a world dominated by uncertainty. Comparisons across multiple Pangaean basins show parallel survival strategies, revealing convergent adaptations in separate geographic regions. Early dinosaurs from the Newark, Fundy, and Argana basins exhibit similar anatomical and behavioral traits despite being geographically isolated. This convergence indicates that selective pressures, climatic stress, habitat fragmentation, and predation gaps produced comparable evolutionary responses in distant ecosystems, reinforcing the theme that adaptability, not size, dictated survival. Fossil evidence also highlights interactions with other small vertebrates and invertebrates, showing a network of opportunistic coexistence. Early mammals, small crocodilomorphs, and amphibians occupied overlapping habitats, competing for resources yet occasionally benefiting from the same refugia or prey availability. These ecological interactions demonstrate that survival was often cooperative or indirectly facilitated, emphasizing the complexity of early post-collapse ecosystems. These survivors laid the groundwork for ecological dominance, quietly exploiting the void left by extinct apex taxa. By occupying niches that giants could no longer defend, early dinosaurs and archosauriforms established the evolutionary pathways that would eventually lead to Mesozoic diversification. Fossil evidence shows incremental expansions in size, range, and dietary breadth, reflecting both opportunity and constraint in an unstable world. Their resilience foreshadows the eventual rise of dinosaurs as dominant terrestrial vertebrates in the Jurassic. By enduring the upheaval, the foundations of a new terrestrial ecosystem began to emerge, even as plants faced their own upheavals in the same unstable world. Palynological records show that surviving vegetation underwent selective turnover, favoring species capable of rapid regeneration and tolerance to fluctuating climates. Herbivorous dinosaurs, already exploiting patchy flora, would soon encounter evolving plant communities, setting in motion co-evolutionary dynamics that would define terrestrial ecosystems for millions of years. In this interplay of survival, adaptation, and ecological opportunity, the smallest and most adaptable players shaped the future of life on Pangaea. Forests on fire, the catastrophe in Earth's flora. Where dinosaurs still roamed, forests trembled under the weight of environmental stress and volcanic fury. What had once been sprawling gymnosperm and seed fern woodlands now faced relentless pressure from repeated fires, atmospheric toxins, and climatic volatility. Palynological records from multiple late Triassic basins show a striking decline in woody taxa, while spore-producing plants surged, rapidly colonizing landscapes rendered unstable. Charcoal horizons reveal layers of incinerated plant material stretching for kilometers, evidence of wildfire intensity rarely matched in Earth's history. In these fire-scarred regions, the vegetation that had defined Pangaea's ecosystems for millions of years began to vanish, leaving fragmented refuges for only the hardiest species. Charcoal layers and sedimentary horizons reveal fires of unprecedented scale, consuming vast stretches of gymnosperm and pteridophyte woodlands. Analysis of these deposits indicates that wildfires were not sporadic anomalies, but a recurring feature of this period, with intervals of combustion coinciding with volcanic outgassing events. Thick ash layers found interbedded with soil strata suggest that eruptions amplified wildfire frequency, turning forested basins into veritable infernos. The distribution of charred plant remains across thousands of square kilometers underscores the simultaneous destruction of multiple ecosystems, leaving early herbivorous dinosaurs scrambling for forage in increasingly barren terrain. Palynological evidence documents a surge in spore-bearing plants, particularly ferns and lycophytes, in the wake of forest collapse. These opportunistic taxa thrived in disturbed soils, exploiting gaps left by decimated conifers and seed ferns. Their spores, resilient to acidic rain and temperature fluctuations, dominated the palynological record for thousands of years, creating monocultures in landscapes that were once ecologically diverse. This spore expansion illustrates the speed and scale of vegetational turnover and provides insight into the selective pressures that reshaped terrestrial flora during Earth's deadliest hour. Early conifers and seed ferns experienced sharp declines, leaving gaps that opportunistic species rapidly exploited. Fossil wood assemblages show a marked reduction in trunk diameter and canopy coverage, indicative of a population struggling to reproduce under repeated environmental stress. Leaf morphologies also changed, favoring smaller, faster-growing shoots capable of tolerating nutrient-poor soils. In some regions, entire forest canopies disappeared within a few thousand years, replaced by low-lying vegetation and fire-adapted pioneers. Analysis of fossil soils indicates nutrient depletion and frequent erosional events, limiting the ability of woody vegetation to recover immediately. The combination of acid rain, volcanic ash deposition, and repeated fires strip topsoils of essential minerals, creating hostile conditions for slower-growing trees. Sedimentary evidence reveals episodic flooding and mudflows, further reshaping landscapes and dispersing plant detritus. These factors combine to prevent the rapid return of gymnosperms, ensuring that opportunistic species dominated for the foreseeable ecological future. Plant morphology shows shifts towards small leaves and fast-growing shoots, reflecting selective pressures for rapid regeneration under unstable climates. These adaptive traits allowed plants to take advantage of brief windows of favorable conditions, reproducing and spreading before subsequent fires or droughts could eliminate them. Fossilized leaf arrangements and branch patterns indicate that these species were highly plastic in growth form, a strategy that increased survival in fragmented and volatile habitats. High-resolution charcoal records suggest that repeated wildfires were a dominant driver of landscape turnover, not merely isolated catastrophes. Quantitative analyses of charcoal content in stratigraphic layers reveal cycles of ignition corresponding to both volcanic pulses and periods of prolonged drought. These recurring fire events prevented the re-establishment of stable forests, maintaining open and highly dynamic ecosystems where herbivores had to navigate patchy and unpredictable vegetation. The planet's crust holds chemical scars, revealing that acid rain and atmospheric CO, two pulses, stressed photosynthetic processes, further reducing forest resilience. Elevated sulfur and carbon isotope ratios in plant material reflect not only volcanic emissions, but also enhanced chemical weathering and soil acidification. These stressors impaired plant growth, limited nutrient uptake, and contributed to the collapse of previously dominant taxa. In turn, this created a feedback loop in which plant mortality amplified soil erosion and altered hydrological cycles. In some basins, spore-dominated assemblages persisted for thousands of years, creating temporary monocultures in ecosystems once dominated by diverse gymnosperms. These temporary ecosystems shaped the feeding patterns of surviving herbivorous dinosaurs and smaller vertebrates, constraining diet and behavior. The dominance of ferns and lycophytes illustrates the profound ecological simplification that followed massive environmental perturbation, emphasizing how plant turnover dictated the fate of terrestrial communities. The interplay of herbivory, climate extremes, and volcanic activity created patchy refugia, where rare surviving plant taxa could slowly recolonize. Fossil evidence shows that pockets of resilient conifers and seed ferns survived in sheltered valleys or on nutrient-rich substrates, providing localized resources for specialized feeders. These refugia represent the tenuous link between pre-collapse forests and the recovery of terrestrial ecosystems in the early Jurassic. This widespread floral devastation foreshadowed cascading effects on terrestrial herbivores, insects, and detritivores, linking land and atmospheric crises. With primary producers diminished, food webs became highly truncated, forcing rapid behavioral and physiological adaptation among consumers. Herbivorous dinosaurs, insects, and small mammals all experienced selective pressures that favored mobility, dietary breadth, and tolerance to chemical stressors. The transformation of flora thus dictated not only survival strategies, but also the evolutionary trajectory of vertebrates and invertebrates alike. Following the silence of fallen forests, the subsequent influx of nutrients into rivers and coastal systems set the stage for microbial blooms in the oceans, bridging the next catastrophic phase of Earth's deadliest hour. Eroded soils, ash-laden rivers, and decaying plant matter delivered massive pulses of nutrients to marine environments, fueling proliferation of cyanobacteria and other opportunistic microorganisms. These blooms would trigger further oxygen depletion, linking terrestrial collapse directly to the next major ecological crisis. In the wake of botanical devastation, both land and sea were drawn inexorably into a chain reaction of biological and chemical collapse, highlighting the interconnectedness of Earth's deadliest hour. The microbial takeover, oceans turn alien. Beneath the once thriving seas, nutrient surges sparked microscopic revolutions among the ocean's smallest denizens, transforming what had been vibrant ecosystems into alien, oxygen-starved landscapes. Rivers, ash-laden and eroded by the collapse of forests, poured an unprecedented load of minerals and decaying organic matter into shallow and deep basins alike, fueling microbial blooms that spread faster than any larger life could adapt. Phytoplankton, cyanobacteria, and sulfate-reducing bacteria exploited the nutrient pulse, reproducing at rates that reshaped chemical gradients and light penetration, while oxygen dissolved from the water column faster than it could be replenished. The ocean, once a reservoir of abundance, became a crucible of chemical extremes, invisible to the land-bound creatures, yet utterly lethal to marine fauna. Oxygen levels, already stressed by these sudden influxes, fell sharply in many regions, creating hypoxic zones that extended from continental shelves to deeper basins. Ammonoids, bivalves, and primitive ichthyosaurs, once dominant and diverse, found their habitats compressed, fragmented, and increasingly uninhabitable. Sedimentary evidence from basins in modern-day Europe, North Africa, and eastern North America reveals black shale layers rich in organic carbon and pyrite, markers of pervasive anoxia and microbial reworking. Each layer chronicles a world in which oxygenated waters retreated to isolated pockets, while sulfide-rich, toxic layers expanded, creating a lethal mosaic of survivable and dead zones across the Triassic oceans. Cyanobacteria and other opportunistic microbes flourished in this chemically altered seawater, forming dense blooms that could be observed as thick microbial mats in shallow basins or inferred through isotopic anomalies in deep water sediments. These mats not only competed with larger life forms for nutrients, but also altered local chemistry, producing hydrogen sulfide and methane that diffused into the overlying water and, eventually, the atmosphere. The feedback loops were self-reinforcing. The more the oxygen collapsed, the more microbial populations expanded, and the more the chemical environment became hostile to metazoans. Paleontologists today interpret these sedimentary and isotopic signals as evidence that microbial metabolism dominated entire ocean basins for thousands of years, creating ecosystems wholly alien compared with previous Triassic conditions. In some regions, microbial mats coalesced into continuous layers on the seafloor, forming structures that modern scientists liken to shallow microbial reefs, albeit dominated by organisms invisible to the naked eye. These mats trapped organic debris, facilitated further anoxia, and provided refuges only for extremophilic microorganisms. Fossilized impressions of microbial filaments, stromatolite-like structures, and mineralized biofilms reveal the extent to which microbial life had become the primary architects of marine landscapes. Larger animals, unable to tolerate low oxygen and high sulfide, either perished locally or were forced into constrained, overcrowded refugia where competition and stress accelerated die-offs. Microscopic scavengers, unseen by any vertebrate eye, transformed organic debris into vast mats of metabolic activity, creating chemical microenvironments lethal to larger fauna. These microbial consortia not only consumed detritus, but actively modified seawater chemistry, producing localized pockets of extreme acidity and hydrogen sulfide concentrations that could fluctuate daily with tides and currents. Geochemical analysis of Triassic sedimentary basins reveals layers of pyrite nodules and isotopically light carbon indicative of prolific sulfate reduction, suggesting that microbial metabolism was driving both local and regional oxygen depletion. Evidence also shows that certain microbial communities formed extensive biofilms that stabilize sediments while simultaneously restricting oxygen diffusion, effectively creating microrefuges for only the most tolerant microbes. These chemical and physical modifications further constrained the ability of larger metazoans to survive, reinforcing microbial dominance in a feedback loop that extended the anoxic interval across Pangaea's shallow and mid-depth basins. Trapped within layers of mud and sand lies evidence showing that these microbial surges coincided with repeated pulses of nutrient input from terrestrial devastation. Ash deposits from Central Atlantic magmatic province, eruptions, eroded soils from scorched forests, and decaying plant matter formed a continuous conveyor of life's detritus into the seas. Each pulse intensified hypoxia, prolonging the extinction interval and preventing any stable recovery of marine ecosystems. Isotopic anomalies in carbon and sulfur from multiple Triassic basins reveal rapid cycling between oxygen-rich and oxygen-depleted conditions, demonstrating a turbulent chemical world that mirrored the atmospheric upheavals and land-based climate shocks. Microfossil analyses further reveal that the composition of planktonic communities shifted dramatically, favoring fast reproducing, opportunistic taxa capable of thriving under extreme chemical stress. Groups such as certain green algae, cyanobacteria, and sulfur-metabolizing bacteria became dominant, while previously diverse communities, including early marine reptiles and nectonic invertebrates, saw dramatic declines. The oceans, once a stage for complex food webs and predator-prey dynamics, had become a microbial domain where evolutionary advantage depended on tolerance to hypoxia and rapid reproductive cycles, rather than size, speed, or predatory skill. Chemical transformations within the oceans reverberated into the atmosphere, linking microbial expansion directly to broader environmental consequences. Methane and hydrogen sulfide, produced by microbial metabolism, contributed to greenhouse warming and atmospheric toxicity, compounding the effects of volcanic degassing and the ongoing climate whiplash on land. Marine oxygen collapse and microbial dominance thus became integral components of the Triassic extinction feedback system, demonstrating how interconnected the biosphere had become. Oceans no longer acted as buffers or refuges. They had become engines of planetary transformation, reshaping chemistry, climate, and the fate of every organism dependent upon them. By the close of this interval, the oceans had fully transformed into vast microbial realms, layered with anoxic waters, hydrogen sulfide, and nutrient-rich blooms that stretched across Pangaea's margins. Once thriving marine animals had been reduced to fragmented, struggling populations, while microbial ecosystems flourished unchecked, altering chemical cycles in ways that would reverberate long after the immediate extinction pulses. The ocean itself, alien and oppressive, served as a mirror to the chaos above. Land burned, air poisoned, and seas converted into a dominion of microorganisms. In the wake of this microbial takeover, all three domains, land, air, and sea, were intertwined in a final crescendo of environmental collapse, foreshadowing the extinction's ultimate and most lethal phase. The final pulse. Earth crosses the threshold of survival. Under an ash-choked sky, the last vestiges of Triassic forests collapsed under the weight of heat and fire. The central Atlantic magmatic province had entered its climactic phase, and vast sheets of basalt poured relentlessly across Pangaea's landmasses, consuming habitats that had endured for millions of years. Palynological studies reveal a near-total collapse of gymnosperm-dominated forests, with spores and charred pollen forming dense layers in sedimentary deposits, signaling that only the hardiest, fast-reproducing plants would persist. Fire scars embedded in silicified wood and charcoal deposits indicate that repeated conflagrations occurred in rapid succession, leaving landscapes sterile and barren. These terrestrial catastrophes were mirrored in the rivers, which now carried ash-laden waters and toxic compounds downstream, affecting coastal and inland freshwater ecosystems alike. Tectonic upheaval unleashed rivers of molten rock that scarred the continents irreversibly. The flow of flood basalts reached thicknesses of over 1 kilometer in certain basins, as revealed by field measurements of the Newark and Fundy basins, reshaping topography while simultaneously triggering local earthquakes. Radiometric dating of dike swarms shows that the pulses of eruption occurred in discrete episodes, each spanning tens of thousands of years but overlapping in some regions, creating a near-continuous barrage of lava and gas. The immense heat released altered local climates, causing short-term spikes in temperature that compounded the already extreme greenhouse conditions from accumulated CO2. Geological evidence from paleosols indicates rapid subsidence and soil sterilization, rendering the landscapes inhospitable to virtually all terrestrial life. Chemical tides surged through the oceans, turning once vibrant reefs into lifeless strata. Sediment cores from eastern North America and northern Africa reveal repeated black shale layers, rich in organic carbon, marking intervals of widespread marine anoxia. Hydrogen sulfide concentrations, reconstructed from isotopic signatures of sulfur-bearing minerals, show episodes when the oceans became lethal to most aerobic life. Calcifying organisms, including bivalves and early marine reptiles, abruptly vanish from the fossil record in these layers, while microbial mats and cyanobacterial deposits proliferate. The sudden shift in redox conditions not only eliminated numerous species, but also disrupted nutrient cycling, leading to cascading ecological failures that would last for millions of years. Locked in the chemical memory of rocks, isotopic anomalies in carbon and sulfur reveal the extreme volatility of the planet's final pulses. Measurements of delta to the power of 13c and delta to the power of 34s in Triassic-Jurassic boundary sediments demonstrate rapid swings consistent with massive carbon injection and widespread sulfide oxidation. These geochemical signals coincide with the timing of camp eruptions, linking magmatic activity directly to global environmental stress. Atmospheric modeling based on these datasets indicates that surface temperatures increased by as much as 8–10 degrees Celsius over relatively short geological intervals, while ocean acidification further stressed marine calcifiers. The combined effect of thermal spikes, acidification, and hypoxia produced a planet operating far beyond the bounds of biological tolerance. Skeletons of vanished species lie entwined in sedimentary layers, testimony to the swift breadth of extinction. Fossil assemblages in North America, Europe, and Northern Africa show that apex predators, large herbivorous archosaurs, and many aquatic taxa were abruptly reduced or entirely eliminated. Teeth marks on fossil bones reveal that scavengers, including early dinosaurs, fed opportunistically on the dying fauna, underscoring how food webs collapsed and restructured in real time. These records also reveal selective survival patterns. Smaller, more adaptable species, both vertebrate and invertebrate, persisted in refugia, highlighting the interplay of physiology, ecological plasticity, and sheer chance. This uneven survival set the stage for a profound evolutionary turnover, where new lineages would emerge from the ashes of the old. A pall of volcanic haze enveloped the land, blending heat, acid, and particulates into a lethal blanket across Pangaea. Sulfur dioxide released during camp eruptions formed sulfuric aerosols that reflected sunlight, creating short-term cooling episodes followed by rebound heating from greenhouse gases. Particulate matter, preserved in varved lake sediments, indicates that skies were persistently opaque, reducing photosynthesis and destabilizing ecosystems already stressed by thermal and chemical extremes. Atmospheric modeling corroborates this scenario, showing that photosynthetically active radiation may have dropped by as much as 70% during peak eruptions, pushing plant and microbial life to its limits. These atmospheric conditions reinforce the feedback loops between land, air, and sea, accelerating global extinction processes. Simultaneous collapses in land, sea, and air created feedback loops that intensified environmental catastrophe beyond recovery. Rising CO2 and methane from degassing combined with sulfate aerosols to produce oscillating climates, while oceanic anoxia fed back into atmospheric composition through gas exchange. Rivers became conduits of both ash and nutrients, stimulating microbial blooms that consumed remaining oxygen and released toxic gases such as hydrogen sulfide. Terrestrial ecosystems, already stripped by fire and temperature shocks, could not withstand this confluence of stresses. Extinction pulses occurred in rapid succession, leaving virtually no opportunity for species to recover between events, demonstrating the lethal efficiency of interconnected environmental collapse. In the silent aftermath, scorched landscapes and poisoned seas remained as stark monuments to the deadliest hour. Evidence from isotopic studies, sedimentology, and fossil records illustrates that both marine and terrestrial ecosystems experienced near-synchronous crises. Microbial communities dominated newly vacant ecological niches, while opportunistic survivors clung to fragmented habitats. Across Pangaea, the once complex web of life had been reduced to simplified communities, setting the evolutionary stage for the Jurassic recovery. In this final pulse, Earth crossed the threshold of survival. The Triassic extinction had claimed its victims, transformed ecosystems, and left a planet teetering at the brink of renewal. Life would endure, but only after navigating the severest trial in its history, a prelude to the rebirth that awaited beyond the scope of this documentary's deadliest hour. In the shadow of oceans turned alien and continents scorched by fire, the Triassic collapse stands as a testament to both fragility and resilience. where the forces of Earth itself reshaped life in a single, catastrophic pulse. We have witnessed the fall of giants, the rise of survivors, and the unseen hand of planetary forces that govern existence beyond perception. From the ashes of forests to the depths of anoxic seas, life endured, transformed, and quietly plotted its return. The deadliest hour has passed, yet its echoes linger in every living thing that carries the story forward. If this journey through Earth's past fascinated you, don't forget to like, subscribe, and leave your thoughts in the comments below.